Okay, so we are in the eighth week of this course, in the module 8. So, in the last module, in the week 7, we discussed about how to solve ODEs. Those were single variable ODEs. Like we saw different methods, like Euler's explicit method, Euler's implicit method, and and the family of Rangi-Gupta methods. So, and also we saw some inbuilt functions like OD45, how we used to solve our ordinary differential equations in MATLAB. So, this week we are going to see some more aspects of solving ODEs. So, I hope you have watched the lectures. So, in that we have covered about how to solve multiple variable ODEs and also how to solve stiff ODEs like stiff systems. We'll see what is a stiff system is, and and also we have seen a few examples on how we can use OD45, and also there is also OD15, yes, which we can use to solve these multiple variable ODEs. So this is a very standard example. Like this is a very standard example of a spring mass system with a damper. So, so basically, if you have like if you have idea about physics in class 12, or if you are a mechanical engineer or a civil engineer, like probability of you knowing about this system would be high. So a very simple system. It's just like uh, we have this spring mass system uh, which is attached to some kind of rigid, like you can say a kind of a wall. So if you apply force to this mass, some kind of force, this mass will just vibrate, like it will go back and forth. And like if there is damping in the system, it will go back and forth, like it will vibrate, and then it will stop after some point of time. It will come back to rest. If there is no damping, then the system will keep vibrating till again you apply some force to stop it. So that's what it does. Like this is the simple what you can say. This is the governing equation of this system. So it's just the Newton's second law. Like if you know, force is nothing but mass into acceleration. So here all the forces are there. So this is nothing but mass into acceleration. So first derivative of x is the position here. First derivative of uh, uh, position is velocity, and the second derivative of position is uh, accel- acceleration. So d square x by dt square is nothing but the acceleration. And in addition to that, there is also a spring uh, which also exerts force on the body, which is given by kx, and due to the damper, this is c into velocity. So c is the damping constant, and dx by dt is the velocity. So so sum of all the forces should be equal to zero. Then we say that system is in dynamic equilibrium. So that's what this does. And in order to solve this, we need two initial conditions. Uh, one is a displacement initial condition, and the another initial condition. Uh, we also need this initial condition, which is uh, at time t is equals to zero, the velocity is zero. So it is like the here it is given that system is stationary, which is nothing but uh, system is having velocity at this point at time t is equals to zero. So that's why here it is not written, but I'm explicitly writing it because we need two initial conditions. One is the position's initial condition, which is x naught is equals to 1 and x dot of 0 is equals to 1. So we need like we have if we have this equation and if we have these two uh, initial conditions, we can solve this system and we can determine how this mass will uh, how this mass will vibrate. Like we can determine at various points what will be the velocity of this mass and what will be the position of this mass. Like at various points in time. Like as time increases, how it will be uh, in motion. So that's what we can do. Like if we solve this system. So if we don't have the initial condition, uh, then it's like we cannot solve this. Like you will get some integrating constants because like just like uh, because this is a second order system. If you want to get if you want to get x, like you have to integrate it first once, like whole system you have to integrate once and then you have to integrate it again. So two times you have to integrate it. Like if I'm solving it analytically, I am saying it I'm saying here about the analytical system. So if I'm solving it analytically, I should have like two. Uh, I will get two constants. If I integrate it two times, I'll get two constants, C1 and C2. If I want to determine these constants, I should know these initial conditions. So that's why we know. That's why we should know. Like what are the initial conditions? Or just if you want to like uh, imagine like if you want, let's say in this aspect only, like this is a spring mass system, right? If you don't know like how you are like what force you are applying on the system uh, and like I'll just drag this, like this is a spring mass system, I'll just drag this, like this is my initial condition, and due to that, like after dragging it and I'll leave it. So this is the initial position which I'll give, like x naught at time t is equals to 0, x naught is equals to 1. So I'll drag it for let's say 1 centimeter and I'll leave it. If I don't know it, like I cannot give an exact solution of this system. So initial conditions are like very important. So we should know the initial condition to solve the uh, governing differential equations or any ordinary differential equation. If you want to solve it, you should have initial conditions. So this is a second order ordinary differential equation, and let's see like how we can solve it. So here we have seen that how we were solving, how we could solve first order ODs in the last module. Here we have a second order ODE. What we will do here is we will convert this into two first order ODEs. This we will convert into two first order ODEs. And then we will solve these two first order ODEs simultaneously. So, so we know that first thing is we know that dx by dt is equals to velocity. That is one thing. So if I integrate this, I'll get the position. So if I just integrate it once, integrate dx by dt with respect to t, I'll get x position. So one thing is done. Then I have this equation of motion, right? So instead of dx by dt, I'll keep dx by dt is equals to v, and I'll send the this thing. What I'll do now is I'll send m into dv by dt is equals to minus kx minus cv, and dv by dt is equals to minus kx minus cv. Right. Now you can see I have this equation and I have this equation. So, so these two are my first order ODEs, which I have to solve to get the solution of this system. So if I solve these two first order ordinary differential equation, it is same as solving this uh, second order ordinary differential equation. So I can denote this as dy by dt also. So here uh, y is the vector of x and v. So like this also I can do. So so this is the resulting ordinary differential equation initial value problem. And I should have two initial conditions. Earlier we had only this initial condition. Here we will have two initial conditions. So we will solve both the initial first order ODEs, and we will see how it will give the results. So let's see it how we can uh, solve this. So here I'm just defining a function which is a spring mass system. So it will give me the values of this. Uh, I have these two functions, right? So this is my F1 and this is my F2. So this is F1 and this is F2. So this spring mass system function is giving me the values of F1 and F2. So I'll give the value of t and y, and this function will evaluate me and give these values. So both this value it will give. And then like I have defined this, and now I'll use the uh, OD45 function, like inbuilt MATLAB function, which is OD45, which uses the RK4 method to solve this problem. So I have this initial condition, which is 1 comma 0. So 1 is nothing but the displacement initial condition, and 0 is the velocity initial condition. And this is the time span, which means that I want to evaluate it from 0 to 10 seconds. Like I want to see how the body moves from 0 to 0 seconds to 10 seconds. So I'll just call this function like this is the syntax of OD45. In that, I have to declare the variables, which is the primary variable and the dependent variable. Primary variable is t, and the dependent variable is y. So y has here both x and v. So that is taken, and I am I will call this function mass spring t comma y, and then I'll give the time span, and then I'll give the initial condition, and this will give me the uh, solution. So the solution will have the values of t and also corresponding values of y at the t values. So and we will plot the results also. So we will see why this in the first plot we will see how sorry, the displacement is varying. Y solve all rows, and the first column will have just the displacement, and if I, like, let's say if I remove both, like if I remove this, and if I just now just solve it, let's see how it will be. So this is the uh, plot which I am getting. So now you can see that initial condition is satisfying. This red line is the velocity plot. So this red line shows how the velocity is varying. And you can see that we have already given this, we have already written here the initial condition for velocity is 0. So this is given here already. So this is a nice way of checking if the solver is like if your code is like written properly. So the velocity is 0. And here you can see the displacement. This is the displacement plot. You can see here that at x is equals to 0, the displacement is 1. Like we have given this initial value. So both the initial conditions are satisfied. And this is also a dam system because we have given the value of C to be something like that's why like this will go like slowly it will like the mass will vibrate and uh, slowly it will reduce its amplitude of vibration and it will slowly go down and after some time it will come to rest. So both the displacement and velocity will become zero. So that's what this plot shows. Let's say if I just let's say if I just uh, you can say if I just increase the damping. So if I just increase the damping, you can see that the will uh, oscillations will further reduce. So now you can see like it is coming faster, it is coming to rest more like uh, compared to the earlier compared to the earlier plot, this is coming to rest at a faster pace. So both displacement and velocity are uh, becoming zero at a very fast pace. So let's say if I just like take the this value of damping to zero, then and if I run it, now you can see that this is not going to zero because the damping is not there. So the mass will keep oscillating and it won't come back to rest. Like this is just for 10 seconds. Let's say if I want to see this for 100 seconds, uh, let's say how it will. So like even after 100 seconds, this is not going back to rest. Like it will keep oscillating because this is the Newton's second law, right? Like if the body is not exerted by any external force, it will keep its state of motion or state of rest until it is acted upon by a external force. So when we had a damper will try to dissipate the energy and it will come back to rest. So because here I am giving the value of damping to be zero, so the damper is not there. So it will indefinitely keep on oscillating for a long time till if you add some force on this body, then it will stop. So that's what this spring mass system example is. And the same thing, like here I am using the inbuilt MATLAB function, which is OD45. Like obviously, when you solve it, like for your own problems, maybe if you are doing some kind of research or wherever you use it, it is better to use OD45 because it is very optimized uh, inbuilt function. Like you don't need to specify the step size. Here I haven't specified the step size. It will adaptively take the step size depending upon the problem which you have, and it will solve it in a nice way. Let's say if you want to write your own code for RK4, that also we can do. Like in the last week, we have written the same code. Here we have just say made a few modifications like initial conditions we only had here last time we had only y of 1 is equals to y naught. Here because we have two initial conditions, we will first define that uh, y is equals to zeros of uh, 2 comma n plus 1. Earlier we had only n plus 1 comma 1. So here we have two initial conditions, that's why we have to give 2. So each row will have one solution. So the first row will have the displacement solution stored in this y, and the second row will have the velocity stored. And in the first column, we will have the uh, initial conditions. So, and we will use this RK4 RK4 like the formula which we had seen in the last class or the last module in the last week. We had uh, y of I plus 1 is equal to yi plus h by 6 into k1 plus 2k2 plus 2k3 plus k4, and these are the values of k1, k2, k3, k4. So initially you predict and then you correct it. Like we have seen this all, like I have explained this in the last class. Like if you are direct seeing it right now, it will be a little bit confusing, but yeah, it's not that like it's not a very confusing thing to be taken care. Like you, if you just watch the last lecture, you can understand it's uh, nothing but the same thing which we had written. But here, the value of yi earlier we had only a scalar value. Here, this is a vector. Here, yi is a vector, so that's why mass spring. This function mass spring will give us the vector. So k1 will be a vector. So then again this k2 will be also a vector. K3 will be also a vector. Then again the value of y, which means the value of displacement and velocity at the next time step will also be a vector. So which will have displacement and velocity. Y will have displacement and velocity. So all rows means first row and the second row, and it will have displacement and velocity. So the same thing, like this, like if we plot this, so the same thing we are getting. So this is the displacement. Sorry, this is the velocity. The red line with circles, and this blue line with circles is the velocity. Sorry, the axle. Sorry, the displacement. And if I want to like solve this using OD45 and compare with my RK4, let's say I'll just say hold on MATLAB, and here my T span is nothing but uh, or I'll just give this. And I'll plot T solve and solve. And I won't use this. I'll just use some dashed line. Yeah. Let's see. Uh, and I'll just plot instead of you plotting both, I'll just plot the acceleration. Sorry, the displacement. Let's see how it will look. Run it. Oh, this is small y. That's why it is showing another. Um, ah, again, this is wrong. Yeah. Now it will be. Oh yeah. This is yes, it is. It will look like this. So now that's it. Like I'll just what I'll do is I'll just add some damping and solve it. So this is how uh, my plot will look like. Just, uh, so this circle one is used. Circle one is solved using the OD45 function, inbuilt OD45 function, and this dashed line is the one which we have solved using. Sorry, this dashed line is the one which we have solved using OD45, and this the circle one is solved using our RK4, like the own manually written RK4 code. So this shows that these both things are the same. So like we don't like we can just directly use OD45, or we can just use this manually written code. But here you have to like take the headache of defining the step size, all these things. Like but here in OD45 you don't need to give the step size. Like if you just give the starting point position, like starting time and the ending time, which is nothing but the time span, it will take care and it will solve it for you. So depends like how you want to solve your problem. So it's always advisable to use it, this OD45 function, because like it is very optimized, and it will give you better results. Like if you are writing your own code, like you have to take care of a lot of things. So otherwise, like sometimes you won't get a proper solution. So this was about the spring mass damper system. I think we had some practice problem in the, where is it? Yeah, the practice assignment, and also in the uh, this week's assignment also we have, I think. So here, so the same thing they have uh, even like we'll look how we can solve this same thing. Uh, so now you can see here that first they have given this equation, and they have given mass, stiffness of this spring, and the values. They have given two different values of C for which we have to solve. One is the underdamped case and one is the overdamped case. So underdamped, overdamped is a technical term. Like you can, we will see like what is underdamped and what is under overdamped. Like, but it's like you just have to solve it. For C is equals to 2 and C is equals to 10. Like you don't need to do more this. And they have also given the initial conditions, which is x naught is equals to 1 meter. And initial velocity is different here. Like earlier we had 0.0, sorry, initial velocity was 0. But here there is some initial velocity which is minus 0.25 meters per second. So, and they are saying that solve it using OD45, and they are giving this time span like 0.0 to 20, and in the steps of 0.1. So we will see we will how we can solve this. So now what I'll do is I'll just modify this function because I have already written it. So C here, C is given as 2 for the first case. I'm just solving it for the first case. C is equals to 2, K is 1.6, and what is M? M is 5 kgs, so M is equals to 5. So, like whenever you solve, whenever you are going to give, like going to give your exam, be careful that all the things which are given here should be in the same system of units. Like here, kg, Newton per meter, meters per second, everything here, everything given here is in SI units. So I'm just writing it directly. Sometimes it might happen that this might be given in kilometer per hour, or this might be given in centimeter. So, like if you're not alert about this, you might ending up solving the problem using the given values, and like if you are not converting it into proper system, like you will get the wrong answers. So be careful about what are the units given. Like this is a very, like if not in this exam, like in this is a like kind of a trap in interviews, or also uh, in some competitive exams like GATE or some other exams. Like this is a very common trap. You uh, you will fall, like if you are not careful about. So I'll just I'm just giving you a you can say a warning kind of a thing. So here, yeah. So T span is given as 0 to 0.1 to 20, right? Yeah. So we are going from 0 to 20 seconds in the step size of 1. Step size of 0.1. I can just remove it. I don't need to give this bracket also. Yeah. And here the initial conditions, you can see that x naught is equals to 1 meter and the velocity is 0.25. So I will write minus 0.25. So the velocity is, initial velocity is minus 0.25. So now everything is like written according to the given data. Now I will solve it. So let's see how it will look like. Like I'll plot it. So this is how my plot looks like. So velocity is minus 0.25. Initial velocity is minus 0.25, and after that it's going like uh, this is an underdamped system. Like it will go undergo certain oscillations. Like like you can see this as if you see a sine wave like this, like damped sine wave, like this is nothing but an underdamped system. Like it is going to negative and coming back to positive, and then it is going to like slowly going to rest. So this is an underdamped system. And you can also see the displacement, initial displacement is also 1. And it's like this is also, displacement is also slowly decreasing. And the kind of a sine wave you can see here also, like positive, and then it goes to, first it goes from positive x to negative x, and then positive x, and then slowly it will go back to rest. So this is what this underdamped system, the plot for this underdamped system is like. Here they are asking us what is the uh, value of displacement at time t is equals to 1. So time t is equals to 1, I have to determine the value of uh, what is the value of displacement. So here if I want to let's say if I want to find out the value of index in t, this is t solve, right? So in this, I want to find out the value of the index at which 1 second is coming. So let's say, I'll just show this. So you can see here, right? So this is my array of t solve. Okay. So this is the vector of t solve. So these are the times at which the problem we have solved. Like we have determined the velocity, like given the velocity, initial velocity at t is equals to 0, and then we have determined that uh, the velocity, the acceleration and also the velocity, sorry, the displacement and the velocity at 0 0.1, 0 0.2 seconds, 0 0.3 seconds, 0 0.4, 0 0.5, 0 0.6. So like from 0 to 25 we have gone. From 0 to 20 we have gone. So from 0 to 20 seconds. So and the step size is 0.1. So like we are going in steps of 0.1. So at t is equals to 1, so t is equals to 1, I have to determine what will be the displacement happening, displacement that will occur at t is equals to 1. So I should I should first look at this index. So displacement, the index at which time is 1 second is 11 here. So 1, 2, 3, 4, 5. So 6, 7, 8, 9, 10, 11. So this is the index at which my time is 1 second. So corresponding to this, I'll have displacement at 1 second, which will also have index of 11. So I can also I can all like if I want to find out, let's say I want to find out find uh, t is equals to 1. Sorry, t solve is equals to 1. So this find will give me the value of index at which uh, t solve is having a value of 1. So let's see. So okay, so just syntax. This syntax is wrong. I think this is the correct syntax. Okay, let's see how find will look like the syntax of find. So if I have forgot some kind of syntax of MATLAB, and if I want to look for help, I can just use this command prompt and I can type help and whatever the function which you are using. Okay. So now we can see that find the indices of non-zero elements. So I is equals to find of x will give me the linear indices corresponding to the non-zero elements, non-zero entries of A. So okay. So it is saying that x will be a vector, and in it there will be lot of non-zero entries, and you want to find out the indices of wherever there are non-zero entries. You want to find out the positions of that entries. And there is also an example. Let's see. Okay. Yeah. So now, so I have not given. double equal to. So whenever you are type of giving a condition like t solve is equals to 1. So I want to find out the position at t solve is equals to 1. So I have to give double equal to. So that this is a conditional statement t solve is equals to 1. So MATLAB will give me the index at which it is occurring. So so this is the index at uh, 1 second is equals to t solve, sorry, find t solve of t solve is equals to 1. And now I'll find out the value of displacement x is equals to what will be the displacement at x is equals to 1. So it will be nothing but y solve. So this is index of 1s comma 1. And if I want to also find out the displacement at 5 seconds, so they are also asking the displacement at 5 seconds. Same thing I'll do at index at 5 seconds I'll take. So just okay. So I'm not intentionally giving the semicolon here so that I can print these values. Like I don't want to use display and write. So we solve this. So now you can see that x is equals to at x is equals to 1 second. This is my displacement. So 0.6675 and at x equals to 5 second and this is my displacement. So I'll just write this. We'll check if we have done it correctly or not. And minus 0.34. And now we also want to see the overdamped system. So overdamped system, everything is same, but C I have to change here. So the value of C is instead of 2, it is uh, 10 seconds. Sorry, C is equals to 10. I think this is a mistake here. 110 instead of 10. 110 it should be 10. 10 only. And I want to find out same things. Displacement at 195. So again, I'll solve it for the overdamped system. So so this is the plot for overdamped system. So now you can see that there are no oscillations. So it will go simply increase the velocity from negative. It will simply increase, and it will go back to 0. So here also the displacement of the body is also simply reducing and it is going back to 0. So it is not oscillating. So that's why this is called as an overdamped system. So there are no oscillations here. Like there is no sine kind of a wave which you can see in the plot. So that's why this is an overdamped system. Uh, because this is happening because we have increased the value of C. So, and these are the values of 0.085 at 1 second, and this is the zero value at 3.9. So we'll see. Check and submit. Oh, yeah. This 3.7. Yeah, so all the answers are correct. So this is how we can check how we have uh, written our uh, code, and like we can vary the value of c, and if you want to determine the well, like values at some pose some point of time, like you have to first determine the index of that time and then give that index to the solution vector, and you determine the displacement at that time. So this is how we can solve using the OD45 for this spring mass damper system. Now let's I think we have gone through stiff systems also. Uh, yeah. So in the next lecture of this module, we have seen how we can solve the uh, stiff systems, and how we can get their solutions using the OD15s inbuilt MATLAB function. So stiff systems are nothing but systems in which there is like rapid change in behavior of the solution. Like here, like you can see that there is gradually acceleration is sorry, the velocity and the displacements are decreasing. Like sometimes you might see uh, in some systems there is like some high like rapid increase in displacement or velocity, like not only in displacement or velocity but some kind of solution, like depending upon the systems which you are solving, there can be some rapid kind of increase, and then in some region it will be slow. So if you have these rapid changes, so what happens is like you have to very carefully take, like you have to take very small time steps. So even OD45 fails sometimes. So that's why like OD45 which we have taken is an explicit method. So we have seen in the last week like Euler's explicit method. Like for Euler's explicit method, it is not stable at all times. So Euler's explicit method is stable at it's stable till a particular value of step size. Like if you go beyond that step size, it will solutions will not be accurate, and the system like the method will start diverging. So like you have to keep your step size below a certain point. So OD45 is a explicit function. So that's why instead of using like OD45, we can use OD15s to solve stiff systems. So the thing, the magical thing which can like which occurs is like uh, even if you have a stiff system and you are able to solve it OD45, like it will take lot number of steps compared to the OD15s. So OD15s will give you a solution in less number of steps. So it will save you computational resources. Like you don't need to uh, use lot of computing power. Like in like if you are getting solution in less number of steps, it is a very good thing. Like you are saving your time and also computers resources. So that's why like it is better to go with OD15s if you have stiff systems. Like whenever you have stiff systems, you can use OD15s. So like it depends. Like uh, you have to see uh, you have to see how, like if your system is stiff or it is not stiff based on these plots, or like you can also determine this like you will get like in this system, like this is the first this is f1 and this is f2, and I have like kind of linearized it, like instead of f1 f2 I am uh, like like here we can disintegrate into two matrices. This is the A matrix and this is the x1 x2. This is the variable vector. So if this matrix is having uh, eigenvalues like which are very different from each other, like here the eigenvalues of matrix are 100 and 0.01 only. So you can like this is a very huge difference between eigenvalues. Like if you know the I think we have seen it. So if the condition number of this matrix is very high, so then that system is like very stiff. Like if this condition number of this matrix, like condition number is nothing but the maximum eigenvalue divided by the sorry the uh, uh, so, highest eigenvalue divided by the lowest eigenvalue. So that if that is like very high, so then your system is stiff. Like if it is like low, then your system is not stiff and you can use OD45. So here this system is a stiff system and it's better to use uh, our algorithm. Uh, OD15s instead of using OD45. Okay, let's see. I think we had, yeah, this. So this is our function. So here we are giving the a value of a, and also after multiplying it with y, we will get the value of f1 and f2. So fl is nothing but a vector here. So y is also a vector. So that is taken care in this function. Like you don't need to explicitly define it. So and then we will solve this system using OD45. So I want to solve this system, and this is my time span 0 to 200, and this is the these are the initial conditions which I have. So 1 comma 1. So these are already like these are given as in this. So the initial conditions are given. So I'm solving this for 200 seconds. So you can see here. So this, like, if you zoom it, so this is like going, like this part is like rapidly going from 1 to 0. So the blue line is going very rapidly from 1 to 0. So, but compared to this, the red line is like not going as fast as this blue line. So this is a very stiff system. Like this, if I just wanted the solution to this red line, I could have used some higher step size, and I could have solved it. But if I want to solve both of this, like I have to take care of this. So that's why uh, I have to take small step sizes, even though if it is not required for this system. But because this second solution is very stiff, I have to take care of both the things at the same time. So it will take, like you can see, some 2000, uh, 24,157 step size is being used here. Like instead of this, I can, if I simply use OD15s, like the syntax of our OD45 and OD15s is same. Like instead of that, if I use OD15s, now you can see that I'm getting the same solution, but you can see that OD15s is just taking 88 steps. So where is 24,000 and where is 88? Like it is like very good reduce in computational resources. So because this was a stiff system, OD45 was taking large number of like step size was very low. So in 15s, like even with higher step size also, I can solve it. So the same thing, like I'll just do it till just 5 seconds. Maybe I can see. So we can see that it goes from 1 to 0 very rapidly. But this red line is not going that much rapidly. Like it will go like it is going very slowly. So this is a stiff system. So that's why uh, using OD15S would be a better choice. So you can also use this was a diagonal system like which we used like this matrix had just diagonal elements. Instead of that, like we can also have this coupled kind of system, like where we can have non-diagonal elements also filled with some kind of information. So we can use this for that also. So and we have also seen this example of a van der Pol oscillator. So van der Pol oscillator is like a very good example in nonlinear dynamics. So it's just kind of like whatever we had seen earlier, right? Like the spring mass damper system, that was a linear system. And this is nothing but like you can just consider it as a spring mass system, but like spring is non-linear. So then you can kind of get this kind of equation if your spring is non-linear. So this is a non-linear differential equation, and we can also solve it like initial conditions are given and like different values of mu are also given. So let's see how we will solve. So we have given here the mu value. First, we will take how mu is equals to 1, and we have defined x and v. So x is nothing but x dash, and v is nothing but x double dash. Okay. So f value is 1, and this is nothing but like again like we have seen how to convert a second degree uh, ordinary differential equation into two uh, first order ordinary differential equations. So we just take x dot is equals to 1. We put x dot is equals to 1 here, and if like sending just this sending the entire thing to the right side, you get uh, v dot is equals to this. V dot is equals to this, and x dot is equals to v, which we have already defined. So now if I want to solve it, so can just use this the same thing I'll use like says the thing like instead of multivariate function I'll use my van der Pol oscillator, and okay, I can use time span 1, and the initial conditions are 2, and so I'll first use OD45. I'll see how it will solve. So this is how it's looking like I've used OD45 and I've solved it. So this is what my solution looks like. So let's say this is solving like OD45 is taking 129 steps. Let's say if I use OD15 instead of OD45, if I use OD15. So it is giving me the solution, but you can see the number of steps have reduced. But this is not that much like the difference is not that much because the system is not that stiff. Like if I just increase the new value from 1 to 100 here. So instead of 1, I have the new value 100. And first, if I let's say if I solve it using OD45, so this is what it looks like. Like I'll just increase the time. It's like 300. So now you can see that the red line, the red line, which is like some, I think the velocity is like changing rapidly. Like blue is not like that much rapid. Yeah, blue is also changing rapidly. So the both the things are changing very rapidly. Like you can see, this is a very rapid change, very rapid change in solution. So the system has become stiff now. Now you can see that here. Oh my God! Like it is taking 665 steps to solve this. OD45 is taking these many steps. But if I take OD15s, like to solve the same problem, it's solving it, and you can see the solution is also getting. We are also getting the solution, but you can see that it is solving it in 453 steps. So it is saving me a lot of time and a lot of computational references. So whenever you have stiff systems, like it's always advisable to use this OD40, OD15s or like other, I think other methods are also there, OD23s, depending upon the problem. So OD15s is an implicit algorithm. So implicit algorithms doesn't depend on the step size. Like step size can be like you can take very high step size, but still you will get a stable solution. So that's what implicit algorithms will do. But computationally, it might be tiring because implicit methods have to solve nonlinear equations sometimes. So that is a trade-off which you have to take care because OD45, like sometimes it won't be able to give you a solution. Like if your system is very stiff, OD45 will sometimes will just uh, like uh, will just raise its hand and it will give you some kind of error or it will take huge amount of time to solve it. So that's why like for stiff systems we use this implicit inbuilt MATLAB solver, which is OD15. Okay. So that's what we had seen, and I think this is not there. So, like the same, this is also an example which we can solve, and we will see how we can do this one. So, this this is also an example. So, this is also OD45. Like, let's see if we have time, we will solve it like this problem too. But now we will see the predator prey dynamics model. So, so this is like a very good, like a standard problem which you will learn, like if you are learning, like if you are going through some kind of computational techniques course, or if you have taken some nonlinear dynamics course, like predator prey, like so it just captures the dynamics between a predator and prey. Like if you have like a jungle filled with tigers and also deers, so uh, there will be like these tigers will be killing these deers, and like there will be also reproduction in this deers. So how this thing will balance out, uh, like with increase in time there will be decrease in the populations of deer, and like after some time like it will again uh, increase or decrease, how these dynamics work out. So this is given by this Lotka Volterra model. So this is like you want to learn it, like uh, maybe you can see some kind of I think computational techniques course in some model you might see about this, or you can just you can just search in YouTube predator prey dynamics. Maybe you can go through that, like okay. So So this H is the population of H. Here H denotes the population of the prey. So you can say the H is the population of deers here. So this equation dH by dt gives the rate of change of population of deer. Okay, and this equation dP by dt will give the rate of change of population of the predator. So which is nothing but the tigers. Okay, so both depend upon each other. Like if the predator is killing the deers, then the deer population will decrease, and if the deer population is less and the predator is not getting food to eat, this the tiger's population will also decrease. So both are interdependent. So this the right hand side which will give this dependence and independence. Okay, so it's like simple thing uh, like coupling. You can see like the population of deers and the population of predator is coupled here. Like in both these equations, like these are coupled equations, and if we solve this, like we can see how uh, what will be the value of like if you have some initial populations of deer and if you have some initial population of tigers, after some time, like if I want to determine what will be the population of deer and what will be the population of predators or the tiger, I can do it by solving this equations. So these parameters are nothing but like alpha beta are some parameters which define how uh, this dynamics works out. Okay, I can just like define a function function predator function predator prey, prey, and p comma y. The same kind of thing I can do here, like nothing but so here instead of mu we have this all these parameters. We will define it. So we have alpha. So alpha I'm just taking as a, and beta I'll just take it as b. I don't want to write long alpha like something. And gamma is nothing but I'll just take it as 0.5. And delta I'll define it as 0. Okay. This I can give as h and p. My f1 wall is here a into h minus b into uh, h into p. This is g into h into p minus what is it? D into. So now I have defined this function which will give me this value of dh by dt and dp by dt at some points. Okay. Now if I'll solve this for the given initial conditions using OD15. So I want to solve for this time span. So I'll just give t is equals to t span is equals to 0 to 0.12 0 to 0.12 50. This is my time span. Just replace it here. And my initial conditions are uh, 1 and 1. Okay. So now if I plot this, this is how my plot is looking like. So, so initially the value of deer and uh, or you can say the tiger is 1, and then it is uh, like going like this, like decreasing. So it doesn't make sense to go in negative, but yeah. So it's going like it's just you just consider it as a differential equation. Okay. And we are just solving it. So this is how this plot looks like, and this you can see that it is just solving it in 151 seconds. So, and they have asked a few questions. They want to find out what is the value of predator, and enter the value of population of predator and prey at 2.5 seconds and also at 10 seconds. So we'll just do what we had done earlier, where we had done that. This kind of thing we'll do it here. Oh, that's it. So first they are asking at 2.5 seconds. So we'll see at 2.5 seconds. 2.5 seconds, they are asking the value of h and also p. So both are being asked. So this is the value of p. This is at 2.5 seconds. Population of h at 2.5. So you cannot give some notation like this. So I'm just giving it as like 2.5 seconds, but yeah, like 25 seconds, but it is 2.5 seconds. And then we also have to find out at 10 seconds, right? So 10 seconds. So we will first find out the value of index of 10 from t solve 10 seconds, and then we'll give that same thing here. So we also want the value of p also. Uh, so this is index 2, and this is because we have given here except and title. So first index is h and the second index is, so that's why here first is h and second is. So if I just solve it, so these are the values which are there. So now I'll just check if I'm getting whatever the answers which I'm getting are correct or not. Double five six, uh, 0.0067 minus 9.442 and 0.0070. Just submit it. So all the answers are wrong somehow. Something we are doing wrong here. Uh, in- what is being wrong? Uh, okay, okay. So the function is not saved and function I'm different. Okay, it is okay. I have to save this and I have to change the function. Sorry. Hmm, it is, sorry. Now it will give me a too many output arguments. Wrong. Function is not defined properly. Output I have not assigned, so that's why it's problem was occurred. Yeah, now it is solved. Yeah, so and this is the plot, okay? So earlier the plot was wrong. So initially the population of both this predator and prey were one. Initial condition was one, and it is going to increase. It is going to increase. Like I think the uh, blue line is for uh, let's see. Blue line is for, yeah. Blue line is for uh, prey, and the second line is for, yeah, predator. Okay. So you can see that the the population of uh, is like the population of this uh, prey which is nothing but the deer population is like increasing. And after like similarly, like simultaneously at the same time, the this population of this predator is increasing. So due to this increase in the populations of the predator, like there are more predators, and like as the population of predator increases, like now you can see that the population of prey is decreasing. So and then because the predators like don't have enough prey, their population also drops. So and then again the population of prey increases, like the population of deers increase, and due to that again these predators get food, so that's why they again increase the population. So this kind of dynamics goes on. So this is like kind of law of the nature. So it's like this is how it happens. Like now you can see that um, uh, the pop this model of this predator prey dynamics is also applicable to like for this I think the uh, I think the about like pandemic, like how uh, COVID was spreading, like that was also modeled using these kind of dynamics, I guess, if I remember it correctly. This was the one, yeah. So like that's why we saw first wave, then we saw second wave, and then we saw a third wave, right? Like during the pandemic. So that's what it was happening there. And we can also see this in human population also. Like now you can see this few countries like uh, China, I think, has reached the maximum population now. Like China, and after like now it is like uh, seeing a decrease in the fertility rates, like due to that their population might decrease, whereas you can see like India's population is increasing. There will be a time like we will reach our maximum population, and after that there will be a slight decrease in our population, and then again it will increase. So this kind of dynamics goes on. So we can model it using this kind of models like Lotka Volterra model. So very interesting thing which we can learn using this. So all the answers, yeah, all the answers are in the range. So everything is correct. Okay. So we are using here OD15s, and you can see here that it is solving like very efficiently. So like if instead of that, if I have used OD45, uh, let's see if yeah, OD45 is also solving it. So it's not a very stiff system. So OD45 is also doing the same. So that is how we can use OD45, OD15s. Like you just have to solve this uh, differential equations which are given. Like define a function like this and solve it. So nothing very uh, dramatical, very difficult. Nothing is like very difficult here. Okay. Now, I think we have seen this in the next lecture. We have seen uh, another. This was the first problem which was posed to us in the starting of the course, like Dhoni hitting a six with an initial velocity of angle 45 degrees. So if the boundary is at a distance of 75 meters, will Dhoni score a six? So that's what we have to determine. Like if the ball will go beyond the boundary. So if it goes beyond this boundary of 75 meters, like if it goes beyond the distance of 75 meters, it will be a six. Otherwise, it won't be a six. So this was these were the two uh, governing equations which we can derive from this, like using the physics, like we know S is equals to ut plus half at square. We have different formulae. Like after doing all the simplifications, we get this two equations. So d square x by dt square is nothing but the acceleration in the x direction, in the horizontal direction. D square y by dt square is nothing but the acceleration in the y direction, which is nothing but the vertical direction. So both of these are second order differential equations. We have to convert these second order differential equations into first order differential equations, which is nothing but we just take dx by dt is equals to v is the first equation, and then we will replace dx by dt is equals to v here. We will get uh, sorry, dx by dt is equals to u, and we will get du by dt, which is nothing but u dash is equals to minus k. So by making these two second order differential equations into four first order differential equations, we can solve this problem. Okay, so this was the function. Like you can see earlier we had only two, here we have four differential equations. That's why there are four variables. So, and the initial values, the parameter values g and kappa are given in the problem. G is uh, yeah 9.81, and kappa is the like you can determine it using this angle of uh, hitting of this and all these things like something. So you can determine. So and then the values of the functions, first function, second function, third function, all these are given, and this function after evaluating will give me the values of all these functions in the form of a vector. So now I want to solve it. So this is the uh, value of theta and phi and all this, and these are the initial conditions. So u naught, sorry, the x naught and v naught are 0, 0, and then we have v naught, sorry, u naught. So u naught, this is the velocity which at which the ball is hit, and it is hit at an angle of 35 degrees. So if I do v cos theta, I'll get the horizontal velocity, and if I do v sin theta, I'll get the vertical velocity of the ball. So these are my initial conditions, and then I have to solve this. Uh, all the initial condition, I am taking it in a column vector like this: x naught, y naught, v naught, u naught, and v naught. And then I'll call this function and I solve it using OD45. So if I plot it, so I'll get some kind of this. So these are all the plots. So I don't want all this. Like I just want to plot. Like this is giving me the x. This is giving me the variation of x. Like from 0 to I think it is going for 5 seconds. Like from 0 to it's going to around some 120 meters. Like this is the, and then this parabolic curve is the profile of y. So for 5 seconds, like after 5 seconds, it's like nearly going to uh, ground. So all these things, and these other two plots are the plots of velocity, horizontal velocity, and vertical. So I don't want all everything to be plotted. So what I'll do is just just take first two. Okay. MATLAB problems. So this, you can see that this is the uh, position of horizontal position of the world with respect to time, and this is the vertical position of the world. Like it will go like this, and it will come back to ground. So this is how we can plot. Like if instead of that, if I just want to try draw the trajectory of the world, I can just doing this is I'll plot this. So this is the x position, and on the y axis, I will draw the y position, the vertical position. So this is how the trajectory of the ball looks like. So certainly we can see that this is crossing the 75-meter mark, and it is going like, I don't know, it's like 120 meter. So a ball is going to ground after 120 meters. So this will go to a sixth. So this is the trajectory of the ball. So it will look like. So this vertical axis, so the y-axis is showing the vertical position of the ball, and the x-axis is showing the horizontal position. Okay. So this is how we have solved the first thing. Like so, this problem had four variables. So we had to solve four first order differential equations simultaneously. So at the same time, we have to solve four first order differential equations using the OD45 problem. So because we had four differential equations, like we should have four initial conditions also. So we can do it like that. Now let's, I think, where is that? Yeah, this is also an example. Uh, it's like we'll see how we can solve it. The same thing, function. Let's say this, I'll define it as pharma, and I'll define this as f1 and pharma t comma y, right? T comma y. Like whatever we have defined like this, we will define it here also. So instead of h, we have s, x, s, x, and p, sorry, x, x, and p, and we have some parameters which are defined here. So d is some 2.5, and what is the value of inlet sugar concentration? This is S in is nothing but 5, and we have water yx. So I'll just define yx as 0.7 yield coefficient, and yp as 0.3. So I don't care what is this problem is. I just have this differential equation. I just have to solve it. Okay. And there is R, uh, which is nothing but hmm, R is nothing but 25 into S into X divided by 15 plus S plus 0.2 into P. So this is my R, and I have F1. So the first function is D into S in minus S minus S minus R minus D into X plus Y of X into R. So here we have three functions. So I have to define one more function, which is F wall 3, 1 equals minus D into P plus YP into R. Okay. And now I have to solve this using my uh, OD45, OD15. Sorry. So I'll just again use this. I'll save this function first, pharma, and then I have this. So instead of predator prey, I'll use pharma, and so the initial concentrations are given 5, 1, and so these are the initial conditions which are given 5, 1, and 0. And I have to use OD50. And we have to find out these concentrations at these values. So everything is, yeah. Yeah. P span is not given here. Okay. We will take some value. So they are asking up to 10, right? So yeah. So 10 seconds, up to 10 seconds, 2.5 and 10 seconds. So this is yes, and this is X. This is biomass. So X is the biomass, and we have the product concentration at 2.5 seconds. And at 10 seconds, we should have the product concentration. So these are the things which are being asked here. Let's solve this. And now let's see. This is the solution curve which I am getting. So the concentration, which first is the sugar concentration is going down like this. It's going to 0. Sorry, it's going to 2.5. And it is this one is going to 1 point, I think 1.5, 1.25 something. And he's going from 0 to some 0.75. So we'll just check whatever the answers which we got are correct or not. 2.501, and this one is 1.7, and product concentration is 0.7/7. And product concentration at 10 seconds is 0.47426. Something is wrong again. Oh, what's wrong? This is correct. This is somewhere wrong. I'll just use T-span as 0 to 10. Or I'll do increase the step size. Just take the function again. 25 into this is the numerator, 15 plus s plus 0.2 is the numerator. Yeah, this is correct. P 0.25. This one is 5. 5 is 0.7. 5 is 0.7. We do it. Okay. We identity. Everything is correct. Yeah, I think whatever we got is correct also, but I don't know why it's around. Uh, Let's see if I can just go to 50. Yeah, whatever we got is right itself. I think so, but I don't know what's wrong with the solution. Slight variation is there, but yeah. Okay, okay, okay. Initial conditions are wrong. Now, now we are getting the correct solutions. Okay, fine. Yeah, everything is in the range. Slight mistake and everything was wrong. Like, so be careful while you code. Simple thing can mess up everything. So this is how we can solve different problems. So we have seen how we can solve stiff systems using OD15s. Like here you can see uh, uh, we have seen first we have seen I think what the single variable ODE in the last week, and then we have gone to multiple variable ODE. So like simultaneously we have to solve here three differential equations which had all these variables s, x, and t. So here we saw that we solved the four differential equations simultaneously, which had four variables. So in this module, like we have seen how we could solve these kind of differential equations. Like even though like if you have second order differential, you can convert it into a single order differential ordinary differential equation, but just by doing some kind of transformation. And like if you have second order differential equation, then you can get two first order differential equations and you can solve it. If you have a let's say nth order differential equation, then you can get n differential equations, n first order differential equations, and you can solve them simultaneously. So you can get the solution to your questions, whatever it you are solving. So like that, we can go about solving it. So that's what today's discussion was about. I think we are clear about how we have solved different things. If you have any doubts now, you can please ask me. Uh, any doubts regarding this? Can you hear me? Um, Anjali or Nasir or Bhavesh or Abhishek? Uh,
Hello, sir. Good evening.
yeah, Anjali. Good evening.
I want to ask one thing. Like, I am doing my PhD and I have topic like fluid dynamics. So, which ODE type, like ODE 45 or ODE 15, will be more effective for fluid dynamics problem, like Navier-Stokes and nonlinear equations?
Okay, so like depending upon the parameters you have, like you can use both. Right, like here you have seen we have seen this, right? Where is this? Uh, Vanderpool oscillator. Yeah. So if mu was one here, we could easily solve it using OD45. But if mu became 100, because of that, system became very stiff. Okay, that's why OD45 might not be a good thing to use. So you have to go to OD15s. So depending upon the problem and which you have the parameters which you have to determine which solver you have to use. Like you can use both OD45 and you can use OD15s and you can see your and you can compare your solution. Sometimes OD45 will just give up, like it won't solve any, it won't solve your problem and it will give some kind of error, and then you can use OD15s and you might get an answer. Sometimes OD15s also might be not suitable. There are some kind of other things also like OD OD23s is also there. So depending upon the problem, you have to check the lot of things and see OD23S is also a thing. So you can use this also, like your differential equations, stiff differential equation might uh, might need this method. So we have to just do trial and error. Like there is no sure, like I cannot give you a sure shot thing that like for fluid dynamics, this might be a correct way to do. In fluid dynamics also, like depending upon the problem, it varies. Like which solver will give you a good result. For example, in my case, I work on this. I work on dynamics. So whatever we have, you have seen this, right? Like this predator prey models, or you can say this trajectory of the wall, or this spring mass damper. Sometimes this like the Vanderpool oscillator. So sometimes we you like lot of the times we use OD45, but sometimes OD45 doesn't give a good solution. You have the like depending upon the problem which you are solving, you will have an intuition like this is not the correct solution for me. So this might not solve my problem. So you just plot it and you see like okay this is not following the trend, or sometimes OD45 just gives up. Then you know that okay this is not solving. So you go to other functions like OD15s or OD23s. Or another way of finding out is like we had this right. So this is a linear system. Like non-linear systems also you can linearize like this. So you just find out the condition number of this matrix. If the condition number of this matrix is very high, then your system is stiff, and you should use some solvers like OD23s or OD15s. But if this condition number is low, you can use OD45 also. So that's how we can do it.
Okay, sir. Thank you, sir.
Yeah. Abhishek was asking, uh, can you confirm? Sorry, can you please give hint for assignment question to a this was assignment problem or practice assignment? Non-graded. Okay. Hint. There is nothing here. Like we just same thing. Like we have written the function right here, right? So we have to write like that only. So if you want, I can write like this there. Uh, function f1 is equals to chem reactor something you give, and t and y, and uh, here uh, there are k is the only parameter, so k is equals to 0.2, mm, and we have CA, like I'll just give CA is equals to y of 1, C B is equals to y of 2, second variable CB is my second variable, so I'm just giving this y of 3, and CC is y of 2. And now everything is there. I have to define this F1 1 comma 1 equal to 1 comma 1 equal to minus k into CA into CB in power 0.6. And similarly, I can have CB is equals to minus 2k 2K CACB 0.6 again. And you can have again this F1 3 comma 1 equals to minus. So this is just plus K. CACB 0. And I just now I can just use this again or solve still. Can use this. Uh, what was that? I have to find out at 1.5 and 1.7.5. And I have to use OD45 here. Same thing. And instead of pharma, I'll use what was that? Define the function. I'll first save this function as chem reactor, right? Uh, chem. And my initial conditions are 2, 5, and 0. 2, 5, and 0. Okay. And I want to solve for, say, 8 seconds. Okay. And I want to find out for 1.5 seconds. And 5 seconds, I want to find out value of CA, CV, and CC 1.5 seconds. Okay, and I want to find out value of CA at 7.5 seconds. So I'll just give us cannot say, write 7.5 as a variable. So I'm just writing 7. So MATLAB restriction which we have. This is the CA, right? Yeah. So first. So if I solve this, I get these values. Let's check how good are these. 1.0201 and 3.400402, 0.9799, and 0.1770. Yeah. So whatever, like we have solved like this. So that's the hint. So just have to define the variables like this. A parameter is given, and then you have to find out each function like this. 3 functions are there. So this is first function, second function, third function. Okay, F1, F2, F3, and you just solve it like we already did, and we have to find out the indexing of 1.5, and then using this index, corresponding values of CA, CV, and CC can be found. Okay, so this is this is CA. This is CA. So that's how we can solve it. Think that's clear, right? Okay, chalo. Uh, okay, I think today we can stop it here. Thanks for joining. Any more doubts? Any more doubts? Okay, no doubts, I guess. Okay, guys, thanks for joining. See you in the next week. Chalo. You have any doubts, Anjali?
No, sir.
Okay, okay. Chalo, thank you.